Yeah, I'm Felix Domke, and I'm going to tell you about alternative Demoscene platforms, like gaming consoles. So, if you look in magazine these days, you might find some advertisements like this. You will see there is a really cool machine, a really high-speed machine for really low money. So, you could think, hey, maybe this is a perfect Demoscene machine because it has a GPU, it has a fast GPU, and it's cheap and it's available, and yeah. So you could think, let's use this for a demo. If you dig on the internet, you will see that there are development kits. Of course, people have to write games for these machines, so there must be some software to write those games. And there are pretty good tools from the vendors, like Microsoft or whatever. But the problem is those development kits are not for free. You have to pay really a lot of amount of money, and sometimes it's not so easy to get them because you have to be an official developer, you have to go through some program or something. But
could you mention some figures? How much money?
this is a difficult question because...
Sorry, can you repeat the question?
Oh, yes, sure.
Yeah, could you please, mention some figures? How much money, for example?
This is actually a good question, which I cannot really answer. First, because I am not an official developer, so I never bought an official dev kit. The other problem with the thing is, can you maybe answer that? Or? Yeah, he says 10,000 euro approximately. The other thing is sometimes you don't even buy the hardware, you merely rent the hardware. So it's not like something you can buy in a store and just use. However, on a retail machine, those devices which you can buy in the stores, you cannot just execute your code. You can only execute code which is signed by the vendor, like Microsoft or Nintendo or something. And this is because the gaming console vendors, they are pretty afraid of people not giving out any money for their games, like it means piracy, people copying their games. Then they are afraid of people cheating online, because the online gaming market is a really big market, and if some gamers patch their games to have a local advantage over the other people in an online play, this wouldn't be great for the other people, and people would stop using the expensive online service. So they want to stop cheating at all possible measures. And finally, they are afraid of non-licensed developers like Demoscenes or homebrew game programmers or people who are just wanting to use this as a server. So they will put a lot amount of security into their products to ensure that only official software run on these systems. It's now a good question, why are they so afraid of unlicensed developers? I mean, they could be happy about people coding for their systems and using their systems. Well, it's easy. The hardware costs in the production much more than what you pay for it in the store. I mean, the Xbox 360 is now available for $200, and you don't really believe that if you have $200, you can produce such a hardware and deliver it to the end user. There's a lot of more money involved in this, and the vendors are putting money into that, and they are subsidizing the hardware and relying on that people buy games, because games, they cost maybe $50 or something and are just a DVD and a casing. There's a lot of money to make on the games. Of course, you have to distribute that to the game developers as well, but they are making a big amount of money with the games. So if now everybody could just write their own games and distribute them on their own, they would not make any money from there. So yeah, that's why they are so afraid of people who can use a retail machine and code for it. And so the result is that vendors have absolutely no interest in selling hardware for Demosceners. They only came for gamers. But on the other hand, you could think maybe, well, it's security, but security is always broken, so let's break into. Well, they are really putting a lot of security into the systems. It's nothing compared to 10 years ago, where you could remove a chip from the system or shortcut 2 pins. On the NES, for example, there was this lockout chip where you could just, basically remove a pin. This doesn't work these days anymore. The security is really embedded into the system, and it's a really big part of the design of a system. On the other hand, that shouldn't stop us, because hackers always found ways, and it might took longer, but so far the hackers always have found a way around their security systems to allow own code. This isn't as easy as it sounds, but those hackers already did it, so we can profit from it and use their hacks to run our demos. I will first tell you a bit about the Nintendo Wii. I think you all know the Nintendo Wii. It's sometimes dubbed as a GameCube 1.5, which is, not exactly wrong, but not exactly right. Still, it's quite a nice machine. It's got approximately 730 megahertz power PC, which is quite fast for that rate, because it's quite a good design. It doesn't have too much memory, but it's a nice system, and it's actually that Nintendo is not subsidizing their system. It's about the only vendor who are really selling their units for the production price. I don't think they will make much money on it, but they definitely don't lose much money on it. Still, the other things apply, like they don't want piracy, they don't want cheaters, so they also have those security stuff inside. On the other hand, there is a hack, and it's a Savegame Exploit. It uses an available game, Twilight Princess, which is a very popular first-party game. It's made by Nintendo, so this game has a save game vulnerability. I mean, you can patch the save game and the game will crash. And this will allow own code to be executed on that system, on a retail system which you can buy in the store. No need for expensive development kit. You really just need, what do you need? You need, of course, a Wii. You need the Zelda game. Then you need an SD card for storing your program. And that's it. That's all you need. There's no expensive hardware involved in this hack. You really just need the game and an SD card and a Wii. So, wasn't there any security in it? Yeah, there was, and their security scheme is pretty interesting. They have a separate processor doing just the security on the device and handling all the descrambling and the signature verification and so on. But the implementation is so damn stupid that you can actually just set the signature, the RSA signature, to all 0 and do a bit twiddling here and there, and then it will pass as a valid hash. So I'm not sure what they did when they implemented this, but this is really just stupid. And there are a lot of other stupid errors in that security firmware. I mean, it's a security processor, so you think the people would know about buffer overruns or uninitialized pointers and so on. But there are dozens of bugs which are obvious once you disassemble that code. And basically, Nintendo cannot do too much about it. All you need is a way in, and the Wii doesn't have any protection about stack overflows in games. So if you exploit a game, like with a patched save game or something, then you basically control half of the system already, because you have complete control over the main processor, over the PowerPC processor, and can do whatever you want. Still, you don't have control over the security processor, which is a separate ARM processor. It's quite big. Actually, it has some megabytes of firmware, where all the bugs are. And but once you're in this PowerPC mode, you can talk to the security processor and exploit the bugs there, and then you have a full control over the system. So it's really hard for Nintendo to patch this, because they would have to patch a game, and Nintendo doesn't have a method to patch games. Microsoft, on the other hand, they can deliver game updates over their online service, but Nintendo doesn't. And they could replace, of course, the disk at the user, but who would change the disk just to remove an exploit. They could do some tricks with the online update, but there are so many games, and really, the Zelda game was the first game we tried to exploit, and it was the thing we tried to exploit in the save game was the first thing we tried, and it worked. So there's really no protection at all about any kind of broken input data or something. And if it doesn't work in Zelda anymore, you just take the next game. There are so many games. And the important thing here is that the Wii doesn't have any protection about broken games. And it is impossible to force the game developers to write non-broken games in the security aspect, because game developers care about games, not about security. They are not security engineers. They are graphic coders or something. And of course, they might know about security, but they don't. I mean, it's not they shouldn't care about it. It should be Nintendo who delivers a secure system, not the game developers. They should not rely on the game developers, but they are. Well, so let's look at that hack called Twilight Hack. It's a Savegame exploit. Basically, we are just changing the name of Link's horse to a very long name, and once the game tries to display that name, it crashes. And it crashes in a way we can exploit that to run something from even some payload inside the save game. And you can actually, the nice thing is getting the save game onto the Wii is absolutely no problem because you can restore them from an SD card. So it's usually if you want to copy a save game to a friend or something, but it can be used to just download the patched save game with the exploit in it and put it on an SD card, copy it in, copy it onto the Wii, start the Zelda game, start the game will crash, the save game will exploit the save game handler. The exploit will run a loader, which then reads homebrew software from an SD card and executes it. So I have a video for you to demonstrate this. I think you might all have seen a Wii already, so you should be familiar with this. So here, we are copying the save game from the SD card using the Wii interface. It actually has a nice icon too. Of course, that's just stored in the save game as well. So now the save game has been transferred to the Wii's flash memory. The Wii has 128 megabytes of flash. Sorry, 512. That's a bit too early for me. And they're using that for the save games and so on, for some caching and stuff. So basically, you don't need the SD card now for running the save game exploit because it's already installed. You just need the SD card for putting your homebrew on it. So we are now starting Zelda here. This is the game. Now the hack is and this is thank you. So this is a simple piece of homebrew called A Cube, which does display a spinning cube. So how to write code? I mean, we don't have the official SDK. I mean, if we had the official SDK, would it be a good thing to use that? Actually, you could use the official SDK software to develop a game, to develop some program, and run this with the hack. But the problem is using the official SDK is, of course, illegal because it's a copyrighted piece of software and you cannot just copy it, and there's no way to buy the SDK. The advantage of the SDK is, of course, that everything works. I mean, game developers don't want to mess around with hardware, they want to write games. So everything is already done by Nintendo to ensure that everything is working. But isn't it boring? So we better look for an alternative. There is one alternative called libOGC. It's an open GameCube library. Don't panic, there's also Wii support in it now. This is not about the GameCube compatibility mode we're talking always about native Wii mode. But the native Wii mode and the GameCube mode do not differ too much. There are some registers at a different place. So basically the library which was written for GameCube homebrew also works for the Wii if you change some things, if you pass it to the right compile flags. And it comes together with a precompiled cross toolchain. It comes for Windows, Mac OS, Linux, for everything. And it comes including a sample code like that spinning cube. So if you want to start developing for the Wii, just get a Wii, get the Zelda game if you don't already have it, get an SD card, very important. Then download this DevKit Pro, I'm giving you an URL later, and start compiling the example, run it, and then start coding your demo. However, if you compare to a PC, the Wii GPU architecture, I try to give a simplified overview here. Basically, the CPU writes command buffers into the RAM, and the command buffers are the draw commands, basically, and the load matrix load commands and the frame buffer blit commands and everything. All what you need, what you want the GPU to do, you write it into a command buffer in memory, and then you program the GPU using some few registers to point to these command buffers. And then the GPU will process these commands, and if it's done processing the commands, it will issue an interrupt, or you can poll forward. And basically, you write the whole frame into the command buffer, then you can do something else on the CPU, and the GPU will render the frame and do everything on its own. The textures are also on RAM, of course. The RAM on the Wii is either it has 24 megabytes of very fast RAM, which is internal to the chip, where it's right next to the GPU. It's a separate die, but it's in multi-chip package, so it's very fast. And then it has an external 64 megabytes of normal dual data rate memory, which is also shared by the security processor, by the way. And you can put the textures into either of them. And yeah, the GPU doesn't render directly to memory. It does render to yet another internal piece of memory called the EFB, the embedded frame buffer, which is so this is because the fill rate problem is between the GPU and the frame buffer, and of course the textures go to the texture cache. So in a perfect scenario, there isn't much data to be fetched from the slow memory. Everything goes inside the GPU between that embedded frame buffer and the texture cache. And once you have rendered your frame, you don't see anything on the screen, but because everything has happened in that embedded frame buffer. So the last thing you need to do is to blit this embedded frame buffer into the external frame buffer, into the XFB, and this frame buffer gets then actually displayed on the TV screen. So this is just a difference to what you might be used from a PC or something, but it's not that complicated, just something you need to know. And if you know this, I think you will understand the A-cube example quite easily because it's not complicated code. Yeah. So this is the project URL. I'm giving you later again a URL where you can download my slides, so you don't need to write this now. So otherwise, if you're able to use Google, you will find it as well. So this is one platform which is very interesting because it's widely available, doesn't require an expensive hack. However, the Wii doesn't have the most powerful hardware. This is a design decision by Nintendo. They wanted to build something which is not too expensive, which doesn't produce too much heat and so on. But face it, it's superior to other systems in terms of raw performance. And we're Demoscene, so we want raw performance. So let's look at another platform, the Xbox 360. The Xbox 360 is a beast. It has 3 cores, 3 PowerPC cores with 3.2 gigahertz each. It has a half gig of RAM, which is quite large for gaming console. Again, this thing retails for $200 or euros. So it is really a lot of technology put into this piece. If you compare to the Wii in the terms of raw performance figures, it's really a lot faster. The GPU is also very cool. It has shader model 3 and even more. It has a very strong fill rate because of the internal design of the GPU. And yeah, it has again some embedded RAM where it renders into. So yeah, let's hack it and have some fun like we did on the Wii. I mean, the Wii was easy to hack, so let's hack the 360. Well, it wasn't that easy. Actually, we started hacking the Xbox before, and it took a lot longer time because Microsoft already had the Xbox One, and the Xbox One, if you remember, was used for a lot of things, but nearly not for games. I mean, you could use it to run a media center on it. You could use it to just copy millions of games to the hard disk and run them from there. So this was really becoming a big problem for Microsoft because the Xbox One was hacked so easily. I mean, there was some security and Microsoft thought, oh, it's enough, nobody will look at this. But some people did look at that and found it ridiculous. And so there was a hack which was quite easy to do. There was a software hack in the end where you could reflash your BIOS from software and so on. So this is all stuff Microsoft wanted to avoid for the next project, the Xbox 360. So the put a lot of effort into the security. The CPU, for example, is a custom CPU, not unlike the Wii. The Wii has a standard IBM CPU. IBM will not tell you that this CPU is directly used in the Wii. They will tell you the one is a 750CL and the other one is the Broadway. But in fact, these are the same CPUs. They used off-the-shelf hardware at last for the CPU. Microsoft developed a custom CPU in cooperation with IBM. Well, IBM developed it, Microsoft paid for it. And they implemented things like memory encryption in it, and they implemented real possibilities so that they don't rely on the games to be not broken. So if you exploit a game on the 360, you don't gain anything from it, because a game cannot write executable code into memory. This is absolutely impossible by the design, because the executable pages are flagged as read-only, and there's a hypervisor which ensures you cannot change the page tables and so on. And they have memory encryption, so you really cannot change the page tables. And they have a small piece of software called hypervisor, which is their security processor. It runs just on the same CPU, and it's just in a different context. But the hypervisor will ensure that games cannot load additional code. The hypervisor will ensure that only signed code can be executed. In short, if you hack the game, the controller doesn't care about it. What you need to hack is a hypervisor. And the hypervisor is like 128 kilobytes of code, and it's extremely well written. I mean, there are checks for everything there. There is a memory range check, which is like one page of code, which is just checks if a given memory range fits into what is expected to be fit. So you cannot try things like having negative lengths and so on. This is everything checked for, and we looked a lot of this code. But to make a long story short, there was one single bug we found, and we could exploit it. And so we developed a hack called the King Kong shader hack. It's basically less relying on the King Kong or on the shader, but more on a single bug in the hypervisor, which was patched in a later kernel version. So what you need is a very specific kernel version. This is the greatest downside of this hack, because if you play a newer game, the game will update the firmware on your system, and you can deny it, but then you cannot play the game. So if you go online to Xbox Live, it will also update your firmware to the newest version. So this is a problem, but you can either buy an old Xbox, which still has an old kernel. There are a lot of old Xboxes around. Or what you can do is to get an additional piece of hardware which you can solder into the device, which will then downgrade your Xbox during a quite complicated procedure, which is another smaller bug which was found. Actually, those two bugs are the only bugs we found so far in the security system, and we were looking for that since over a year now. So basically, it is possible to downgrade an existing Xbox. On the other hand, if you run a new game again, it will re-update the box. So you basically need a second Xbox. This is sad, but it's that way. Also, the really newest versions of the Xbox don't run anymore with the hack, simply because they had some hardware changes which require a new kernel than that kernel which is exploitable, and the exploitable kernel won't run at all on that new hardware because they have a different CPU now. But there's a large base of Xboxes around, and if you really look hard, you will find an Xbox with an old kernel. And so this is ugly, but it shouldn't stop you from coding, really. What you also need is a modified DVD-ROM firmware, because you need to patch a game, and of course the game is on a pressed disk, so you cannot modify it. Instead, you need to burn a disk like the Evil Wares guy is doing. So we need their hack, a modified DVD firmware, to run a patched game. Of course, we own the game, but we still need to do a backup with some patching inside. And we will basically write the game then to a recordable disk and boot that game. The hack is available. You need an image of the King Kong game. Then there's a patcher which patches in the exploit code, and then you need to run that game. So what you gain with this hack is an arbitrary code execution in the hypervisor context, which is something you don't even get on the SDK. The SDK, I was told, has the same security in place as the retail machine is. The only thing different in the SDK is that the signing key required to assign user space applications is included in the SDK, but you cannot just run Linux on the SDK because there are exactly the same security stuff implemented on the SDK. On the SDK, you cannot write a just-in-time compiler because you cannot write code to memory because this is part of their security. There is another thing called another user mode, which is a sandbox in the system, which is used for that original Xbox emulator, which runs on the 360, which runs original Xbox games. It's basically a real emulator for the original Xbox. But this isn't really, an SDK won't gain you as much as the hack would. Sure, the hack is a bit more complicated to use, but with the hack you have full control over the system. On an SDK, you are still forced to use all that Microsoft stuff. You're forced to use their software, you're forced to use their kernel, you're forced to use their hypervisor, their memory layout, and so on. So, yeah, we ported Linux to the 360 just as a proof of concept that we own the hardware now. Yeah, so I will demonstrate this now. How to boot the hack. The Xbox is basically, I've bought it in a normal shop, I've patched the DVD firmware, and I've upgraded it to the correct kernel version. It had the very first kernel version, which was not yet exploitable. There's only one, or exactly two, kernel versions that are exploitable. The older ones are not, and the newer ones are not. But in the middle there are two versions, which are, so I've updated the system to that. And yeah, I will try to show you how that works. There's one thing, the hack doesn't work all the time. There's an ugly bug somewhere and nobody yet was able to find it. So if it doesn't work, I just have to retry, but it usually works. I would bet it doesn't work today, but let's see. So this is normal 360 booting. I'm now inserting the special patched game. Yeah, it's put to German, I don't know why. It wasn't my fault. So it will now do the authentication of the disk and run the disk. Due to the patched firmware, my copy will authenticate. So it will now run the King Kong game. And we just want to play the King Kong game. But oops, what's that? Now there's a black screen and the DVD-ROM opens, so I can put another DVD in which contains the code I want to execute, in this case a Linux kernel. And this is a part where it sometimes doesn't work, but this sounds good. Or does it? Takes a few seconds and either it works or not. Yeah, it works. So this is now Linux booting on the yeah. Ignore those error messages. Yeah, so it takes a moment without network. It will take a bit longer, but don't panic. I can otherwise just continue with my talk right now. So yeah, let's do a hello world. Or better, let's write a winner demo. Let's display a spinning cube. I mean, that's what we want, right? So again, we don't want to use the official XDK software, the SDK for the Xbox. We cannot even use the official XDK because the hypervisor is not running anymore. The Microsoft kernel is not running anymore. It's just our code running on the machine. And code compiled with their software, I was told, really needs that kernel functionality for some stuff. They do most hardware access actually from the games directly, but they rely still on a lot of kernel functions for memory management and so on. So basically we cannot use the XDK. This is, again, nothing which should stop us because we have a lot of drivers developed for the system. I mean, Linux is running completely. We also have an accelerated GPU driver based on reverse engineering. Basically, we took a game and dumped the command buffers again and tried to make sense out of it. And with some help of reverse engineering the functions, we found out how most things work. We started to play with, we first started to replay the command buffers from the game, and then we started modifying those command buffers, like injecting new vertices and so on, until we figured out enough to make actually sense out of it. And we now have a nice library which allows you to use the GPU. There's a downside, well, it's not really a downside, but the GPU doesn't have a fixed function pipeline anymore. It really just have shaders, so everything you need to do must be done in shaders. And shaders are written in the high-level shader language originally on the Xbox. If you are an official developer, you have to write your shaders in that language. And there is a quite complicated compiler which produces a shader microcode. And that shader microcode is quite complicated because it works around some hardware bugs maybe in the GPU. It works around some register dependencies and so on. It's really not easy to compile this shader. But there's a good thing, because of course we won't use the XDK software, but Microsoft does offer you XNA. This is something where you have to pay for it, like $100 a year or something, and then you can use C# and .NET and all that Microsoft tools to write games. The downside of this is the games run on a retail system, so this sounds pretty cool at the first moment, but you're forced to use C#. You cannot write C code or C++ or reuse any code. You cannot write assembly code. You cannot reuse, of course, existing code you have written. And it's not really what I thought homebrew should look like. Some people are actually liking this, and it's good that there are some people who are using this, but it wasn't what I think of homebrew should be, because homebrew is also about freedom, and you want to use the tools you want to use the language you want, and you certainly want to code assembler if you want to code assembler. And all that's not possible with that XNA stuff. But that XNA stuff also allows you to use shaders, of course, and there's a shader compiler included there. So we can just use that. It's wrapped in a .NET library, but somebody wrote a wrapper around it to use just the compiler without the rest of the system. You don't need to pay the $100. The software is free. It's just the $100 if you want your Xbox to execute that stuff, but you don't. You just need the shader compiler. So we rip the shader compiler from that stuff and use that with our shaders. If we look at the very simplified Xbox 360 GPU architecture again, we see that it's quite similar to what the Wii already had. We have again the GPU with that embedded memory. It is 10 megabytes here compared to the 10 megabytes compared to the 2 megabytes in the Wii. Actually, the Xbox 360 has a very large fill rate thanks to that embedded DRAM, which is direct next to the GPU die on the same chip package with a really large and fast bus, because it has to go about 1 centimeter and not real length, because it's so tied to each other. And that makes a lot of the performance of the 360, that it has that embedded memory. That, on the other hand, this means if you render something to that, you don't see it on the screen immediately. You have to, again, to put this into the external frame buffer. It's called resolve. You can use textures from RAM. You cannot use textures from that EDRAM. The GPU, of course, also has some caches, but I haven't put them in here. The procedure is nearly the same again. You put your command buffers into RAM, you tell the GPU to execute that, and the command buffers, for example, load then the shaders from RAM, they load the textures they set up the texture fetch stuff, they set up the vertex fetch stuff, and so on. And the GPU will render that into the embedded into the embedded DRAM, and will then at the end, you need to resolve it with a frame buffer to actually see something. That embedded DRAM is actually not simple RAM, it's a quite intelligent RAM which handles the Z-compare and the alpha blending. So the GPU really just need to push the pixels into there, and the EDRAM will do the rest. This is a real advantage, because the GPU doesn't have to read anything from the EDRAM. It just have to write stuff in there, and the RAM decides if it wants to drop this or blend this or whatever. And I said at the end you need to do that resolve operation to actually see something. The Xenos, the GPU is called Xenos, it's their code name. It has a shader model 3 and a bit more. For example, it has the memory export functionality. You can for example, in a vertex shader, you can you only use your output data for a pixel shader or for rasterization. You can also write that data back to memory. So you can use the GPU as a general purpose processor processing lots of data, which is quite cool because the GPU does everything in float internally, and you can use 32-bit float textures. You can have, if you want, a 16-bit float frame buffer or even 32-bit frame buffer if you restrict yourself to 2 channels. So you can do some image pre-calculation, for example, which usually has to be done on the CPU using expensive CPU operations like a saturation add on something. You can do this in the shader and write it to memory. Or you can process vertex data that way. You can process your bone loops or whatever on the GPU directly, write it back to memory, and then reuse it from the CPU if you want, or reuse it in multiple vertex shader. So this is a pretty cool feature. I'm not sure how many games do use that feature, but our exploit uses that feature to actually write to memory and trigger the exploit. So that's why it's called the King Kong shader hack, because it actually uses a shader to write to the memory. So again, we want to display the spinning cube. What we have to do is to first initialize the hardware to map the memory, upload some microcodes, which are extracted out of the original ROM image. Then we have to load our shaders into the to make it. Yeah, the GPU needs to use shaders for everything, so you need to upload them once. And then for each frame, you usually set up the material, you draw the primitive, and at the end, you resolve everything to frame buffer. So the API we developed during the version engineering, well, we have seen that the GPU actually was developed with Direct3D in mind. I mean, it was developed especially for the 360, but it's amazing how the hardware looks like. It really looks like a Direct3D interface implemented in hardware. There are some enumerations which match exactly, for example, the compare enumeration and so on. You just write them into a register and then it's active. So Direct3D is quite a thin layer between the actual hardware and the user space. They are doing some compatibility stuff to work around some GPU things, some things which are really different than the Direct3D model. So we simplified this a bit, and our low API is really a low-level API which directly works on the hardware and no fancy compatibility stuff inside and so on. But it looks and feels like Direct3D, not because it was done by reverse engineering with Direct3D drivers, but more because the hardware actually looks like Direct3D. So if I say we have a low-level API, this might sound very complicated to use then. And we don't have any unnecessary indirections or wrapper. So you might think that things are getting very complicated, but I try to tell you about this anyway, so yeah, you can either understand it or not. So the first important thing is we need to initialize the hardware. Now in the perspective of I'm already running Linux on it, and I now want to write the spinning cube. So we need to initialize the hardware. This is quite complicated because the shader hack left the GPU in a quite unstable state, because basically we are abusing a shader feature, and we have to do everything this, and this is the actual code to do this using the library. This is very complicated, as you can see. So what it will do is to map the memory IO registers, do all the initialization and so on. And as the next thing, we need to define a render target, and we just use the frame buffer as our render target. The render target is basically just 2 things. Just the scaling, the resolution, which is rendered into the EDRAM. It must be obviously rendered into the correct resolution. We don't want to scale when we resolve. And we already also said where it should resolve the stuff into in terms of a memory address. So it doesn't do much here, it just defines where to put the rendered data once we resolve. Okay, we need our cube. Here's our cube. And I think everybody who already displayed a cube knows what this is. This is the vertex buffer, and this is the index buffer at the bottom. Basically, we defined a vertex buffer format here, which is, it has a lot of things which we don't use in this example, but why not? It doesn't really hurt. However, we need to tell the GPU how the vertex format looks like. And actually this is done, the vertex shader needs to know how to fetch the vertex data. So what we do is to describe our vertex buffer in a simple structure where we say the first thing are 3 floats with the position, then there's the normals and so on. And yeah, it's actually the same thing as in Direct 3D on Windows. Then we need to put our geometry into physical memory. We using something here which is called vertex and index buffers. It's the same thing as in Windows again. Basically, we create the buffer, it will allocate some physical memory. We lock the buffer, so we can access it from the CPU. We copy our geometry to that. We unlock the buffer, it will flush the caches for us and so on. And basically now we have a vertex buffer, which we can use in drawing. Same for the index buffer. Again, same thing as in Windows. Now we need to load our shaders. The pixel shader is easy, we just load it from disk and put it into physical memory. There's a specific thing on the vertex shader, because the vertex shader has to access our vertex buffer. And the vertex shader is patched after loading to load the correct vertex buffer format. So we need to apply some patches to it. There's a function to do this. You just have to give it the vertex shader and the format you want, the vertex buffer format you want to use. Then it will patch the shader so it fits with that format you're using. So you can use an arbitrary vertex buffer format. You just have to call these functions to modify the shader, and then it will work. Our vertex shaders actually this year, it's quite easy. We are just transform the position into normal and pass through the UV coordinates. Actually, we want to display a cube with a texture on it. Why not? So we are using some, it's really not complicated stuff here. And we want to have some lighting, that's why we need the normals. And we are compiling this shader through with that XNA shader compiler hack to microcode, and our example will use that microcode then. The pixel shader is also a very simple one. It just has a directional light and does a texture fetch and multiplies that and puts it into the frame, into the pixel. So nothing complicated. Now we want to render the frame. First we need to invalidate the state, which basically means to set up all render states to the default values. We need some, I have done using some fake GL. It's not real OpenGL. They just named that way. We are using, set up some model view matrix and fake model world matrix for the normals. And so we can actually spin our cube. I mean, we have the GL rotate, which does rotate the cube. And we have the GL translate, so we want to move the cube a bit further into the Z direction. So we are not inside that cube, but in front of the cube. Then we need to set up the direction for the pixel shader, the light direction, which is just the pixel shader constant. Again, there's a simple function that a pixel shader constant. The matrices are vertex shader constant, so you put them into the vertex shader constant. We are setting the shader we want to use. We are setting the stream source, the vertex buffer. We are defining the stride of the vertex buffer, which is 12 D words. We are setting our index buffer. We are setting our texture. Because we don't want to generate a texture, we just use the frame buffer as a texture because it's there and it's usable. Why not? It can, of course, also create a texture before and fill that with some useful data. Then we will do the draw index primitive, which is also very similar to the direct 3D function. So we will actually draw the primitive. You, of course, can draw more than one primitive. You draw them all into the embedded DRAM. You then, at the end, resolve that thing into the real frame buffer, which gets displayed onto the TV. And finally, you wait for the GPU to finish. You can do this more intelligent by preparing the next frame already, but in a simple example, we just wait for the GPU to finish the frame. And yeah, that's basically all you need to display a spinning cube. I mean, if you compare this to a Windows, the Direct 3D program, it's actually as simple as it is on Windows. So I can demonstrate our nice spinning cube, which we have developed now. You can actually compile your code directly on the Xbox, so you don't need any cross compilers or something. So I will just log in.
Did you use a special distribution or
I can repeat his questions. He asks if I'm using a special distribution for Linux. Oh,
Did you use a special distribution, or if yes, which distribution, and or build it from scratch?
no, actually you can use any distribution you want if it provides PowerPC support. I'm using Debian because I like Debian, but other people are using Ubuntu or whatever. And basically you can use whatever you want. You can also build something from scratch. But I think the Xbox is such a powerful machine that you don't need a specialized distribution for it. Usually, on the Xbox One, for example, you had a special distribution because of the limited size of memory, because you wanted to strip out everything which isn't as important. The Xbox One had 64 megabytes of memory. But we have half a gig and we can afford just running any distribution we want. Of course, if we want really to just display a demo, we might strip everything away except the demo. We could run the demo as our only process if we want, or we could even strip away the Linux and write the demo directly on the without any operation system. But no, to answer your question, this is Debian, but you can use whatever you want, provided it has a PowerPC port. But most decent distributions do have that. It can be either a 64 or 32-bit port. I would suggest using the 32-bit port, because 64-bit for PowerPC is in user space. It doesn't gain much, and it's a lot more complicated. Anyway, yeah, I have already compiled that demo. It's really not more than I have shown before. So, yeah, this is the demo, and it displayed a spinning cube with the frame buffer pod and a texture on it, and has the direction lightning. And this is what you get for that simple code. So. Now you can start coding your winner demo, and yeah, it's really as simple. I hope as it is. I will put the slides. I have stopped it now. I will put the slides on my website, which is also linked on the seminar page, so you can download that library there. You can download the slides there with the example program in it. And if you have questions, you can just, of course, ask me, email me, or there's also an IRC channel. So we are nearly done. Yeah, basically we are done. If the beamer, oh, I did it again wrong. 2 black cables are too complicated for me today. Yeah, so do you have any questions you want to ask me? Yeah?
I'll just wait for the microphone.
Okay. In the meantime, these are some URLs you might want to visit, either for the Wii stuff or for the 360 stuff, or for the stuff I just told you about. Again, I will link this on the seminar page, so just follow the link there and you will get that stuff. Yeah?
Okay, so for the Wii exploit, is it likely that we would need to write our own NOP slide type loader, or is it likely that we'll need to write additional loaders for additional games if you can't get a hold of that particular Zelda thing? Or is it difficult? Is that source available? In other words, if you can't get a hold of that gosh darn game, how do we get our own code to load?
Basically, we could, of course, the exploit we now have is pretty fixed to Zelda, to the addresses Zelda uses, to the bugs Zelda uses. But if it would be, of course, possible to develop another exploit based on another game. It shouldn't be too complicated. It's just a matter of coding. And actually, things are looking very good, so we soon have a homebrew channel which is installed into the system menu. So you just need to run the Zelda hack once, or whatever hack you want to use, if there's another one. And then you will have a homebrew channel installed in the system menu, which just runs your code from SD card. So I think there will be soon new methods to run code. Right now, the Zelda game is the easiest hack, but there will be plenty of other hacks soon, I guess. There's also the possibility to resign an original disk with a different executable, but you need a drive mod chip for that then and burn the disk each time you want to change something, but this is also possible. I think this will get patched quite fast from Nintendo. So the game exploit really has the advantage that Nintendo cannot really easily patch it. But there will be more exploits, and there's no need to panic if you don't like Zelda. If that was your question. But Zelda's a great game.
Yes, but okay. Was that actually a GameCube game or was that a Wii game?
This is a Wii game.
Okay, because I have several other Wii games, you know, sports and so forth.
Yeah.
But I don't have that one, and I would like to, rather than going out and buying that one specifically to get started, I'd like to use one of the 4 games that I actually have.
Sure. So actually, if you just mentioned it, Wii Sports is of course an interesting target because nearly everybody has it. So we might put some effort into developing an exploit for Wii Sports. Zelda was the game, the original coder for the exploits there it was just playing Zelda, so it was already in the drive, so that's why I used that game. Yeah, and we thought it was important to not hack a third-party game, but a first-party game, because Nintendo might get angry with the developers. Of course, my position here is that game developers shouldn't need to care about security, but we don't know how Nintendo is thinking about it. So we thought if we hack a Nintendo game, it's their own stuff, and they cannot be angry at any third-party developers, because if it's a small third-party developers who know if they get problems from it, and that's what we definitely don't want, so that's why we took such a large game. Yeah, another question?
Did the existence of those versions of Zelda, the Wii one and the GameCube one, had anything to do with finding the hack?
Yes and no. Basically, at the time when we started developing that hack, we already could decrypt Wii DVD images. So there wasn't. You are right. There is a GameCube version of the same game, which has nearly the same code. It was originally a GameCube game, which got ported later to Wii. Yeah, the save game stuff is a bit differently because on the GameCube you have those memory cards, which you cannot so easily patch. And no, actually we just used the Wii version of the game because we already had it, and yeah, it includes symbols as well, so it's quite easy to disassemble. Yeah, anything else you want to know? Otherwise, yeah, you can go to my website and get the stuff there, or write me an email if you have a question, or visit me at Breakpoint in row in the 17 or something. On the right side, third row, you will, I think, see the Xbox. Yeah, so that's it. Thank you for listening. And yeah, I would really love to see some more console gaming demos in the next demo compo. So it would be really great if some of you start coding a winner demo now, not only using a spinning cube, maybe a bit more, but yeah, thank you.